To a passenger, the sky outside the window looks like completely empty space, but an aircraft is actually moving through a dense, heavy fluid, one capable of ripping an airframe apart if its physical limits are exceeded. To maintain steady lift, a plane relies entirely on predictable fluid dynamics. The wings need smooth, laminar airflow to keep the aircraft suspended, but the atmosphere is constantly churning. These hazards represent localized zones where the fluid predictability of the air fails entirely. To safely navigate the planetary boundary layer, a pilot has to learn to identify, visualize, and map these invisible aerodynamic boundaries before flying into them. We can separate these disruptions into three distinct threat vectors: thermal instability, topographical disruption, and mechanical shear. Mapping these invisible boundaries allows a pilot to maintain structural and aerodynamic integrity when the atmosphere becomes volatile. In meteorology, stability is defined very specifically as the atmosphere's resistance to vertical motion. Under standard conditions, temperature decreases steadily with altitude. This standard lapse rate naturally keeps the air layered, predictable, and relatively calm. The anomaly happens when a mass of air cools at a rate faster than that standard baseline. It becomes unstable, loses its resistance, and triggers rapid vertical convection. Look at this diagram detailing the convection process. Notice the blue upward arrow. As ground heat warms the air, it expands, cools, and rises, creating a powerful updraft. The cycle completes as surrounding air cools, generating descending pressure, seen as the red downward arrow. This basic thermodynamic loop, warm air rising and cold sinking, is the physical foundation for the most destructive convective structures on Earth. When thermal instability is fed by high moisture, it builds a thunderstorm. The first phase is the cumulus stage, which is dominated entirely by massive, continuous vertical updrafts. You can see the physical evidence of this rapid vertical expansion in the real world. These billowing cumulus cloud masses are the visible markers of immense heat and moisture being thrust directly upward into the atmosphere. As the updrafts continue, the cell enters a transition phase. The cloud mass reaches its maximum density, and its vertical growth accelerates. Looking at this late-stage cloud formation, you can clearly identify the dense, heavy white structures indicative of this transition, right before the internal moisture becomes too heavy for the updrafts to support. Once the precipitation begins to fall, the storm enters its mature stage. The falling rain drags air down with it, creating violent shear zones against updrafts that can exceed 3,000 feet per minute. It generates severe squalls, hail, and intense icing conditions. Finally, the storm reaches the dissipating stage. The updrafts choke out, and the cell is dominated predominantly by powerful downdrafts, causing the top to flatten out into a distinct anvil shape. This image captures the definitive markers of a highly dangerous mature cell. The flattened anvil top shows the storm hitting the upper limits of the troposphere, while the dark, heavily shadowed base dumps massive amounts of water and concentrated downdrafts toward the ground. Because of extreme structural loading, severe turbulence, and the risk of catastrophic engine water ingestion, aviation rules dictate a strict operational mandate. Thunderstorms must be avoided at all costs. But violent turbulence doesn't only require thermal heat. Solid terrain can mechanically disrupt high-speed winds, creating invisible hazards like mountain waves. These waves develop under very specific conditions. When winds blow at 25 knots or more perpendicular to a mountain ridge, the terrain physically forces the air mass upward, creating smooth upward currents on the windward side. To a pilot, this deceptive updraft carries the aircraft smoothly over the peak, masking the danger. But as the air crosses the peak, it plunges down the leeward slope, violently following the terrain contour, creating immense downward pressure. This initiates a series of severe wave-like oscillations extending downwind. The most severe turbulence occurs right here, in the spinning rotor zones that form in the dips beneath the wave crests. Pilots can sometimes spot physical warning signs of this mechanical shear: stationary, lens-shaped lenticular clouds, or distinct roll clouds often mark the exact location of those turbulent wave crests. Terrain also funnels concentrated masses of cold or warm air. These katabatic winds rush down the slopes, accelerating to localized speeds of up to 50 knots, creating intense shear close to the surface. This is why flying in mountainous regions without specialized instruction carries serious consequences. The intense leeward turbulence and downward pressure can quite literally overpower a plane's climb rate, pushing the aircraft directly into the side of the mountain. Topography isn't the only trigger for sudden aerodynamic shifts. Wind shear is broadly defined as any sudden change in wind speed or direction over a short distance, occurring either horizontally or vertically. One of the most critical zones for shear is right near the ground, often during periods of strong temperature inversions. Imagine an aircraft stabilized on a precision approach glide path, descending toward the runway. As it drops through the inversion layer, it crosses a sudden boundary where the high-altitude winds are severed from the calm air below. The aerodynamic consequence is immediate. A sudden decrease in headwind strips the wings of their relative airflow, resulting in an instant loss of indicated airspeed. Without the altitude to recover, the aircraft can abruptly stall and fall below the glide path. The aircraft themselves also tear the fluid apart. Wake turbulence is a mechanical byproduct of lift generation, trailing behind any heavy aircraft. The strength of these trailing pair vortices peaks when an aircraft is heavy, clean, and slow. As a large jet rotates for takeoff, the high pressure under the wings spiraling up into the low pressure above creates two distinct, violently spinning tornadoes of air. These unseen vortices are heavy and persistent. They sink at a rate of 300 to 500 feet per minute, and once they hit the ground, they spread laterally across parallel runways at 2 to 3 knots. Surviving wake turbulence requires strict spatial discipline. If taking off behind a large jet, you must rotate before their rotation point and fly above their climb path. When landing, you maintain a glide path above theirs and touch down firmly beyond their point of contact. Mechanical shear and wake vortices are uniquely dangerous because they strike exactly when the pilot is lowest, slowest, and completely devoid of the altitude margin needed for a recovery. Ultimately, what we call flight hazards are really just localized breakdowns in fluid dynamics, driven by severe thermal heat, immovable terrain, and the mass of the aircraft themselves. Because these aerodynamic boundaries are completely invisible from the cockpit, a pilot has to map them using external data. You cross-reference low-level prognostic charts, onboard radar sweeps, and live reports to build a mental model of the air ahead. The pilot report, or PIREP, remains the primary real-time tool for identifying exactly how violently the atmosphere is churning. Read the clinical meteorological definition of severe turbulence on this chart. It is specifically logged when occupants are thrown violently against their seatbelts, accompanied by a momentary, complete loss of aircraft control. Maintaining safety relies on using precise meteorological data to maintain strict geometric separation from these volatile environments. Professional airmanship relies on the intellectual discipline to visualize the invisible, and to understand exactly when and where the predictable stability of the sky will fracture.